Hi students, I want to continue on with the equilibrium discussion with another example. It's called the common ion effect. I seem to have a little trouble spelling. Sorry this is so slow. Yeah, so sometimes if you add something that is insoluble to a solution that already contains one of the ions in the insoluble compound, so that's called a common ion. It's an ion in common with what you already have. It's going to affect the solubility of the compound you're trying to dissolve, and that's called the common ion effect. Really, really common also. How many times can I say common in the AP exam? So I wanted to give you an example of it that I found in Zoomdall. So you can look at the 6th edition and see what you see. Okay, so the example is calculate the solubility. Oops, I hate it when that happens. I'm going to get rid of that little selection tool. Give me a second. I will get faster, I promise. But at least I know how to get rid of it now, I think. Oops. Well, bear with me. Okay, so we're going to calculate the solubility, the molar solubility of this insoluble compound, which happens to be calcium fluoride, when it's in a solution of sodium fluoride. So I'm copying this problem out of the book, and I think I probably don't need to write so much. That's probably my problem. Bear with me. We'll get better. I think I have gotten better. You may not think so, but my blood pressure is certainly better while I'm doing this. Okay, in a solution of, okay, now I'm reading the example, 0.025 molar sodium fluoride. Okay, now hopefully I'm not going to write all this out, but you know calcium fluoride is insoluble, and you know that sodium fluoride, since it's got a group 1 cation, is completely soluble. So it's going to be a source of fluoride ions. The sodium fluoride is going to supply fluoride ions. The sodium is going to be a spectator, and the calcium fluoride, as it dissolves and then starts to dissociate, it's going to see, whoops, I already see some fluorides in there. Ooh, maybe better run back and get out of here. Anyway, let's look up the KSP of calcium fluoride, and I just looked it up in the table. You can look it up in the table too. Nobody knows these things unless they measured them. As I said, they measured them during the last Great Depression. So 4 times 10 to the minus 11 is the solubility what am I talking about? Is the equilibrium constant for this, and since it's a solid, it's called a KSP, as a solubility product. Okay, now I'm going to write out everything I just said, which I wish I wasn't doing. But in case you forgot, sodium fluoride is a group 1 compound. Sodium is group 1, so what you get from that is sodium ions and fluoride ions. And you're not interested in the sodium ions. They're spectators. You're interested in the fluoride ions. Or you may not be interested, but the calcium fluoride is interested. Okay, so, oops, now I'm writing I'm making a mistake. So the sodium fluoride, which started out initially as 0.025 molar, completely dissociates into 0.025 sodium and 0.025 molar fluoride, and I'm going to catch that in a minute. I can see myself catching it. I'm going, oopsie, I meant 0.025 molar and 0.025 because that's what the problem said, and you can't just make up a number. Maybe it's good for you to see this happen because it's easy to do when you're working a problem. You know, those zeros are annoying, but they really affect your answer, and I've seen it happen to you, and now you've seen it happen to me. Okay, so there's your common ion, the fluoride. I just put initial and final. That F doesn't stand for fluoride. Now see what I'm going to do. So I'm going to say the calcium fluoride is the Okay, it's the one with the KSP. Why does it have a KSP? Because it's the insoluble compound, it turns out. Fluorides are mainly insoluble. I know we didn't learn that, and then here, doggone it, if every example that you find, it doesn't involve fluoride. So we're just going to write. I'm not proud that I've been taking this long. Not ashamed either. Ta-da! Look at that. Now that's cute. That was worth waiting for, wouldn't you agree? Okay, here comes the pencil. What's it gonna write? Okay, molar. So molar ice table. Yes, indeed. This is teaching me I don't need to write everything in the world. So calcium fluoride solid dissociates into the ions. That's the direction you write it. Okay. Now again, not many ions, otherwise we wouldn't even be doing this problem, would we, boys and girls? Initially, change in the equilibrium concentration, it's a solid, I don't have to write anything there. Initially, I don't have any calcium, nothing dissolved, but, ooh, sitting in a solution of sodium fluoride, and there's plenty of fluoride in there. Plenty of fluoride. More fluoride than I'm going to get from the little calcium fluoride when he does his best to dissociate. So he's going to dissociate, and he's going to give me the same amount of calcium moles per liter as the amount of him that dissolved. But I'm going to get twice the amount of the molar solubility of the calcium fluoride. So when I do my final accounting and add my initial and my change, together for the calcium and the calcium fluoride, I get 0.025 plus 2x for the fluoride. So the KSP quickly turns into an ugly thing. And not ugly yet, it's just calcium times fluoride squared. So it's equal to calcium times, oh, I bet I make a mistake here. Oh, hello, dear students. You're not going to believe this, but this is the second time I'm recording this tonight. I forgot to press record. Now, I'm just hoping that... oh, good. There's the little pencil. Hi, little pencil. I'm so happy to see you. Let's see what you're going to write. You know, I have such an appreciation for what students go through because... it's so hard the first time, isn't it? I know. I love you, and I empathize. Well, anyway, that's enough of that mushy stuff. So KSP, I told you I looked it up before, 4 times 10 to the negative 11th. And I said I'm going to try to ignore that X. Not the X that's the calcium, but the X that is the fluoride that results from the dissociation of the calcium fluoride, right? So that's 2 times 0. It says 0.0250 plus 2, it looks like 20 or 2, but it's 2 times 0, and then I square it. So I'm going to just say, oh, I think that's X times 0.0250 squared. And I don't think I don't like the quadratic, so I'm going to just solve this. And believe me, I didn't die. I'm looking for my calculator, and I'm plugging it in, and I'm calculating 0.0250 squared. Oh, and I believe I've successfully calculated it now. And it's 6.25 times 10 to the negative 4th. Yippee! And I better remember to put times x in there. Oh, my goodness, look at this. Look at this woman. She's crazy. Okay, there she goes. Times x. I mean, that's the variable you're solving for goodness sakes. How can you forget to put it in? So x is going to equal the KSP, right? Divided by dun, 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 the fluoride ion concentration squared. I've even forgot to put the negative, right? Now, that was called the expression. Notice no numbers in there. When they ask for the expression, they're asking for the variables, okay, that x over what? Then when I substitute, I get that 4 times 10 to the negative 11th divided by 6.25 times 10 to the negative 4th, which is 2.50 squared. I mean, 0.0250 squared. Now she must be looking for a calculator. How could she lose it so quickly? I mean, my God. And then all you have to do is, I mean, it's going to be 10 to the minus 8th. Come on. 6.4 times 10 to the minus 8th, right? Okay, I think an imbecile could figure that out. And that's x in molarity. Naturally, I didn't put the units down there, but I should have. That's the concentration, and didn't even put the chart. Okay, calcium plus 2 concentration, and it's also equal to the molar solubility of the calcium fluoride, because the calcium fluoride and the calcium concentration produced are the same, because there was no calcium ion in solution when you put it in there. There was only fluoride ion from the sodium fluoride. So that's the molar solubility. When you put calcium fluoride solid, just throw it in a beaker, take a bunch of that crap in my hand, I throw it in there, and that solution contained 0.025 moles per liter of fluoride already. Notice I put a little square around the final answer. I said that equal x. I wish I would have said that equals a molar solubility, because on an AP test they would have loved that. Now, what I'm trying to do is prove here with this little less than 5% is that I didn't need a quadratic. So you should do that. If you don't use the quadratic equation, and I don't know, I hate it. Maybe that's something left over from my childhood. It's probably easier to use on your computer now. But I can prove that if that number x, which is the numerator, 2 times 6.4 times 10 to the negative 8th, that's 2x, and that's the number I was ignoring with respect to the 0.025. So if that number divided by 0.025 times 100 is less than 5%, it was a good thing to ignore it. Okay? And it is. Look, it's not even, it's 0.02%. So it was much less than 5%. You'd be an idiot to go through all that business of a quadratic. You'd get the same answer, right? So that's why I say it was okay to ignore with respect to 0.025. So you should prove that. Okay, don't forget to do that as your last little step. So no quadratic necessary. Now, I know there's some students that love the quadratic, and I guess on your calculator it's very easy. Once you set up your equation to put it in a quadratic, but it's much faster for a lot of us to just estimate. This is called successive approximation. We didn't even have to do it because it was much less than 5. I'll tell you about successive approximation later. This was just a first approximation. It was swell, I tell you. So swell, it's all swollen up.